Can people hear me online now?
We can, thank you.
Okay. Okay.
Reintroducing you to Peter Diener online. I did this before, you couldn't hear me. We are coming back to our sessions, to our talks, and we're going to have Peter Diener talking to us about Sphinx BSSN, relativistic hydrodynamics using particles.
Sorry about hiding over here, but you can probably see why I need to sit down. Yeah, so today here I'm going to talk about something that is actually not in the Einstein toolkit, but it has stolen pieces of the Einstein toolkit at least, so somewhat relevant. So what I'm going to talk about is Sphinx BSSN, relativistic hydrodynamics using particles. This is an effort that we're working together with Stefan Rosbrook in trying to get SPH methods to be used for general relativistic hydrodynamics. And this is something, well, I mean, we've been working on it for some years, but it's still fairly new. So first I will say a little bit about what it is, and then I will talk a little bit about why do we need another relativistic hydrodynamics code. We have plenty out there, but we can never have enough. I will tell you a little bit about smooth particle hydrodynamics. I will show you the BSSN equations, but we have seen them already here in this, so I won't, but I will highlight a few things there. Then when you're doing particles and space-time evolution on a grid, then you have to have a coupling between them, and I'll tell you in a little bit about how that is done, because that is really important in order to get things to work. I will show you a few test applications, a special relativistic shock tube, just to show that SPH can handle stuff like that. And then some results for stable TOV stars. And then go on to a few astrophysical applications that we have worked on, some BNS binary neutron star mergers with a long-lived remnant. I will show some result with a binary neutron star merger where one of the neutron stars is fastly spinning, and also show that we can do binary neutron star mergers that ends in collapse. And I will end up with some outlook and future developments. So Sphinx BSSN is a relativistic smooth particle hydrodynamics code that is coupled to a grid-based space-time evolution code. And so that means that instead of discretizing your matter variables on a grid, you represent them, you split them into individual particles that has a certain mass that stays constant during the evolution, that move wherever the hydrodynamics and gravity equations dictate. And in this code, space-time is represented on discrete points placed on a fixed mesh refinement 3D grid, and it evolves according to the full nonlinear Einstein equations. And as the name implies, the formulation we use here is BSSN. Oops, went too far. So Sphinx BSSN is targeted towards astrophysical systems where the matter is warping the space-time significantly and thus cannot be treated in either Newtonian limit or in a fixed background space-time. So things like binary neutron stars, black hole neutron stars, and stuff like that. So accretion disk in principle as well. So why do we need another relativistic hydrodynamics code? And the main answer is diversity. SPH codes use a Lagrangian approach to the hydrodynamics, which is very different, and it's always good to have different codes with different methods so we can compare results and make sure things are done correctly. So in order to emphasize this, I just written down a few a few information, a little bit of information about Eulerian versus Lagrangian codes. So in Eulerian codes, the quantities are attached to fixed grid points, whereas in Lagrangian, the quantities are attached to particles that are moving with the fluid. And so that means that in Eulerian codes, you have the changes of quantities at a fixed grid point, so you can treat, you just have partial derivatives of your fluid variables. In Lagrangian, you have change of quantity within the moving fluid parcel, so we have a Lagrangian derivative here. So for an Eulerian code, the resolution you have is completely determined by your grid spacing, whereas for Lagrangian code, the resolution follows where the particle goes. So when particles go together, you just have higher resolution, which is essentially what you want. And so one point is that with Eulerian methods, it's kind of hard to adopt to changing geometries, whereas this comes naturally in Lagrangian approaches. And so if we look at binary neutron star mergers, then we know from GW 170817 that such binaries will produce gravitational waves as well as electromagnetic counterparts in the form of kilonova. We certainly hope that we will see more of those in the future because we can learn much from them. So the gravitational waves are produced by the bulk matter motion, whereas the electromagnetic radiation are produced by the small amount of matter that gets ejected from the system. And this can be over the order of just 1% of the matter, of the total matter in the system. So one point is that Eulerian codes have issues with the surface of stars, and we have seen some examples of that during this workshop, and therefore have to employ an atmosphere in order to keep the high resolution shock capturing schemes happy there. And this can lead to sort of unphysical outflows of low density material. And it can also, in principle, lead to that any real outflow you have after interacting with the atmosphere is getting affected by that, and it might be more difficult to understand what the physics is. And in order to really understand these multi-messenger astrophysics systems, it's really, really important to accurately describe the ejecta so that you can make a connection from the observed kilonova signals or whatever back to the gravitational signals that is produced by the merger. And so here and this is not to pick on anybody in particular. I just found these plots in a paper by David Ratchicher and other people, where they evolve a binary neutron star system here with just a polytropic equation of state with a certain mass. And you can see this is the initial data. And as the two neutron stars evolve, orbit each other, you have all of this low density material sort of appearing between the stars. And it gets worse and worse, and you can also see the neutron star surface getting kind of fuzzy. When you do SPH, you don't need an atmosphere at all. And so just for comparison, I took one of our simulations. It's a different system, but it should still illustrate it. And this is what our neutron star looks like. So we have two neutron stars in orbit around each other. They orbit around several orbits. And you can see just before contact, there's essentially nothing going on except for where the stars are. And you can also see that the the neutron star surfaces are quite well behaved. These things here are essentially just an artifact of the visualization tool. At this point, like we do have some outflow, so there are some particles in this region, but they are really low density, and the visualization software has a hard time sort of rendering that properly. So this is one of the things that we expect to be one of the main advantages. We don't need an atmosphere, and hopefully for that reason we can really trust our ejected material, the outflows coming from them, and make connections to kilonova signals. And just to emphasize, so this is essentially the same plot as that. Here we color code things, we made sort of a isosurface codes here. But here I show individual particles, and as you can see, there's absolutely no particles escaping the stars until they actually touch each other, and you actually have some ejected material. So as I mentioned, Lagrangian codes are very good at adapting to changing geometry. And just as an illustration of that, I found this this simulation by Stefan Rosvoog. This is not full relativity. This is Newtonian gravity for the self interaction of the star in a background of a Schwarzschild black hole. And let me go here and stop the movie. And so in this movie, the black hole is always located at the origin, and you can see there's some change in the scales here, so the black hole is now up here, and you actually have part of the tidal deformed material that or ejected material that actually comes back around the black hole and eventually will intersect with itself as it streams in and out. And as you can see, this is only a partial disruption, so the core of the star survives and is still self-gravitating, and this is all handled. This changing scale in geometries are handled beautifully by SPH codes. So I'm just going to let it run here. So this would be a simulation that would be very difficult to do with a grid-based hydrodynamics code. Of course, now that we're actually coupling the hydrodynamics to a space-time evolution on a grid, we still have a grid for that part. So we lose some of that flexibility, but in principle, when we get further on and makes the code more flexible, we should be able to use the hydrodynamics to refine our grid in places where we need to. So prior SPH codes have been limited to Newtonian gravity, or either Newtonian gravity or static background spacetimes, or the conformal flat approximation to general relativity. So this is the first code that managed to combine SPH with full evolution of the spacetime in general relativity. So smooth particle hydrodynamics, what is that? Well, as I said, the basic idea is to replace the fluid by a finite set of particles, and each particle move with local fluid velocities. And each particle has kind of what we call an interaction radius, or the smoothing length, where it actually sees the effects of other particles within that radius. And you assign a smooth kernel function, I call it here W, that in order to estimate the density of a particle of the fluid at a given position, you can do a sum over the neighboring particles multiplied by this kernel function to get the density. Each particle gets assigned a mass, and that mass is constant during the evolution. So by default, we have conservation of baryon mass. We don't have to worry about anything with changing that, except for when we actually have a black hole forming or particle escaping our space-time grid. And in Newtonian theory, if you don't have gravity, you have exact conservation of both mass, energy, momentum, and angular momentum if you write the space equations correctly. So, as I said, matter is described as particles with mass ma. So the mass can be different for each particle, but we typically want to keep the particle masses as similar as possible. We don't want particles that have 1/100th the mass of somebody else, because then they get very jittery and can do all kinds of weird things. And as I said, we then calculate the density at a given particle location simply by doing a weighted average over the neighbors of their masses times this kernel function. In the Newtonian limit, you can actually write down a Lagrangian simply like this, where you have the kinetic energy and the internal energy, and then you can just derive the evolution equations from that, and they become this form here, where again rho a is just the density, and you get that the time derivatives of the velocities and internal energies are given by expressions where you just have to sum for a given for particle A, you have to sum over its neighbors of terms that involves derivatives of this kernel function that can be and those derivatives can be evaluated one time at the beginning, and you can just have a lookup table where you look them up. So many people say that SPH codes are very dissipative, but this is something you can control if you do things very carefully. And my colleague Stefan has studied this extensively, and he's probably one of the best experts in making SPH methods as accurate as possible. So many people use standard cubic spline kernels, and they typically result in a lot of noise being generated because you only use a few neighbors, and so things can change quickly when particles are moving around. But he found that if you use kernels that require more neighbors, can reduce the noise significantly, but of course it comes at a larger computational cost, because every time you have to sum over your neighbors, you have more neighbors to sum over. You do have to add some dissipation or artificial viscosity in order to handle shocks, and these then depends on differences in particle velocity. But you can and you can just use the particle velocities at if you look at particle A and particle B, you can look at the difference in velocities, and that will give you some amount of dissipation. But you can also use slope limited reconstruction to the midpoint, between particles to reduce the dissipation where you have smooth flow. In addition, you can also use entropy measures to steer dissipation that can further reduce the amount of dissipation applied. And sure.
So I can envision this thing
really amazing as neutron stars are spiraling and after merger. But at the point of merger, when the neutron stars are touching and there's even shear, how do you measure how much the errors are compared to the Eulerian? I see the Eulerian code may be better in that situation, or would you argue that it would be at least as bad?
Okay, so Zach is asking what happens when if you have a binary neutron star, when the two neutron stars actually start touching each other, where you of course have shocks developing. Yeah, well, I mean, I can't say for sure whether, I mean, that one of the other would be would be more accurate, but I can say that Stefan made a lot of tests, especially for Kelvin-Helmholtz instabilities, and you can get very finely resolved Kelvin-Helmholtz instabilities, and we also see that when we actually have we do see very clear Kelvin-Helmholtz instabilities appearing, and they get sharper and sharper as you increase the number of particles. So I don't think there's any problem with that. But I mean, I can show you some things later on. No, it's just, but the particles get closer to each other, so you have higher resolution automatically. No, we don't add more, but as the particles get closer together, you automatically have a smaller smoothing length. I should probably say that in our simulations, we always we adjust the smoothing kernel dynamically through the simulation so that we always have the same number of neighbors within our kernel.
In situations like Zach is mentioning, you keep the kernels spread.
The kernels are, so Pablo was asking if we...
Getting very many. Think that they still work as expected.
Okay, so Pablo is asking if we keep the smoother kernels spherical, or whether we flatten them in regions where things might dictate that is the case, that would be appropriate. And the answer is that we always keep our smoothing kernels spherical, and according to Stefan, that is what in the spherical kernels is what in Newtonian guarantees conservation of linear and angular momentum. And so we don't want to mess with that even in GR when things can be different, when we don't actually have conservation of those quantities because of gravitational waves. So we keep them spherical at all times.
Maybe. And my question, independently of the GR, then why is it that the community or cases, extreme cases of that, has moved away and love that SPH supposed to be sophisticated shock patterns?
So Pablo is asking, so if this works so well, why has anybody else moved away from it? And I don't know why anybody else is doing what they're doing.
For type of disruptions,
yeah.
This problem of collision of neutron stars, I think maybe some comparison will be in order.
Yeah. Well, I mean, I will show you some collisions and later here, and hopefully that will convince you that this actually works.
What happens when you compare other methods with this SPH, not just look at that. And the other thing, maybe this is too technical. Are you going to show us equations in general relativity?
Yes.
Okay.
Okay. So here is just two of the favorite kernels we're currently using. One is called the Wendland C6 kernel. This is this weird function, but as you can see, it's plotted here. It's something where the volume of the kernel when you integrate over the sphere until it goes to 0 is 1. And the green one is these harmonic-like kernels that actually has values larger than 1 at the location of the particle it's associated with. And this might be a problem because when this happens, you could in principle have something called a pairing instability, where something happens when particles gets too close to each other. But we haven't really seen any problems with that in our simulations. So this is probably the one we use most of the time. So by doing experiments, Stefan figured out that the C6 kernel sort of requires of the order 300 neighbors in order to function well, while the W8 we can get around with 220 neighbors. So Pablo was asking about the equations in general relativity, and this is what they look like. Again, you can start from a Lagrangian. You can define your computing frame density. You can define your Canonical momentum per mass as just your Lagrangian divided by the velocity, 3 velocities, and your canonical energy per mass. And when you do that, you get equations that look very similar to the Newtonian equations. You see we have these, well, maybe I should go back here. We have mass, we have P over rho squared times the derivative of the kernel, and so on. And the only difference here is that this derivative depends on the determinant of the metric, of the 4 metric. And then in addition, you get these gravity acceleration terms that ensures that the particles feels the curvature of the space-time. So in addition to these equations, we, like in Eulerian codes, we also have to recover our primitive variables from the evolved variables. And we have to go through the same hoops of solving some nonlinear equations in order to do that. So we have to do some, do whatever everybody else has to do in that case. Oh, the A, that is the particle number. So this is the determinant at the location of particle A. And then the B's are the neighbors. And so you see, it depends on the determinant in both, because we have DIA and DIB here. So that will. Computing frame density, yeah. Yeah, so NA, so the computing frame density gets determined by just summing over the masses of the nearby neighboring particles and its smoothing length. No, the rest mass is this one. That's the lowercase n. So it's the typical relativistic relation between those.
The mapping to the traditional Hydro, which they use this density scale by kind of Lorentz factors. So where is that?
So,
I mean, another way to put it, I mean, these particles are moving.
yes.
They're moving fast. So to compute quantities, if you get multiplied by any of those factors of anything like that, would be.
The computing instantaneous computing frame density just depends on the current position of all the particles of the neighboring particles, and
there is no sort of, because it's Lagrangian, there is no sort of Lorentz transformation from the frame of one particle that is moving to the other one to complete the kernel across?
No, I don't think so. At least, well, this is how it's done in our code, and it seems to work.
Yeah, calculating density from the continuity equation, and you calculate it like just summing the masses, you get the same answer.
I haven't done that experiment, but I don't remember what Lorentz factor we have in our shock tube test. Stefan has done lots of tests. Okay, let me go on. So that's the SPH. Then for the spacetime, we just use standard BSSN, except that more recently we have actually introduced some of Sachs improvements to this, so we add some constraint damping and stuff like that as well. So I probably don't need to talk too much about the BSSN equations here. Well, I should show you what I've highlighted in red is where the hydro equations requires metric information. And then in the BSN equations, I've highlighted in red where the BSN equations need information from the particles. And of course, those are all the terms coming from the stress energy tensor. So let me just skip ahead here. So the problem is that matter information is available only on the particles, and metric information is only available on the grid. And so we started with something fairly simple in the mapping from particles to the grid, but we have that method has evolved a lot from the first implementation. So our current scheme uses what we call a local regression estimate in combination with a multidimensional optimal order detection, which is a bit of a mouthful. But the main idea is that, let's say in this plot over here, we have the grid point where we want to evaluate the stress energy tensor. And then the blue points are particles around it. Then we can expand any function around this grid point by just a normal Taylor expansion, and then use all the particles along with their smoothing kernels to use linear regression to solve for the quantities, the field, the quantity at the grid point, and the derivatives of certain order, depending on what order we go to, at the location of the grid point. So we can actually do that to different polynomial orders. We can do it to 0th order, 1st order, 2nd order, 3rd order, and then we can estimate or calculate an error measure simply by evaluating that the expansion, evaluating that at the grid points and see how much it deviates from the value that we actually have on the particles at that. And again, this is weighted by the smoothing kernel with the distance to the grid point. And then we can simply choose the order with the smallest error measure in order to ensure that we get the most accurate result for the quantity here. Unfortunately, it doesn't work in all cases, because sometimes when you have a particle, a grid point close to the surface of a star, then you mostly have particles on one side, and this can become very inaccurate. So we, in addition, also add a scheme to to detect the situation when we are near the surface of a star. And by essentially evaluating in using our SPH information on the particles, evaluate the gradient of the radius -3, which should be 0. If we evaluate this with this expression from a smooth particle, because we only have particles on one side, we will get a larger error. And this is what I show here on this plot here, where I show this measure on a grid where we have 2 neutron stars located, and you can clearly see where the surfaces are. And so we can use that, and in that case, we can reduce everything to just the 0th order, lowest order interpolation. Okay, go ahead, Eric.
Hi, Peter. I just that expression, the delta A. I just recall that Gundlach uses that expression to define summation by parts operators in spherical symmetry.
Ah, okay.
That may or may not important, but I just recognize the expression. Thanks.
Okay. And so that is the complicated mapping for the particles to the grid. In order to go the other way from the grid to the particles, we simply use 5th order Hermite interpolation in order to ensure that the values, first and second derivatives, are continuous doing that. So this is our 11-step plan for taking one time step in order to not be confused with the AA 12-step plan. So we start by, in a given time step, to convert from the BSSN variables to the physical metric. We can then map the physical metric from the grid to the particles. We can then update the neighbor tree because the particles have moved since the last time, so that we need to find our neighbors. And then we can calculate the local rest frame density. Actually, no, we can calculate the local the computing frame density. And then from that, we can recover the physical hydro variables from the evolve variables. And from that, we can calculate the stress energy tensor at the particles. We already have the metric, and we have all the fluid quantities. And then, so we can map the stress energy tensor from the particles to the grid. Now we have that on the grid, and then we can calculate the time derivatives of the metric variables on the grid. And that will allow us to calculate the gravity acceleration terms that the particles need. And so we map those back to the particles. And that allows us to finally calculate the time derivatives of the hydro variables on the particles. And then we update the time step used based on the minimum hydro and BSSN Courant factor requirements. And finally, we can then update the hydro and metric state vector based on those time derivatives. And then we go back and do it all again. Yes, we have added some constraint damping into the BSSN equations from Sachs' prescription. So, yeah.
There are spatial derivatives of the metric in the hydro equation.
Yes.
Would you also interpolate to calculate also the degree, and then you bring it to the particle?
Yes. So the question is, if we calculate the derivatives of the metric variables on the grid and then map them to the particles, and yes, that is what we're doing, as well as the time derivatives. So if you remember here, we need the spatial derivatives of the 4 metric, and we need the time derivatives of the 4 metric here. And they are all calculated on the grid, and then those 40 quantities are mapped to the particles.
Yeah, but then you have a time derivatives of the metric. No, this is the 4 metric, but
This is 4 metric, yeah.
yeah, you have also matter sources in those equations from the BSSN equation.
Yes, that is why we first map only the metric to the particles, and then we can calculate the stress energy tensor. We map that to the grid, and then we can evaluate all of those quantities, and then we can map the gravity acceleration terms to the particles, and then we can evaluate the right-hand size for the hydro. So we have to do it in this order in order for things to work.
You have different measure requirements, so you have different time steps.
No, in our code, we've simplified things, so we use the same time step everywhere. Yeah. So I don't remember what the parameters was for this shock tube. It's probably not as strong as you were asking for. But Stefan has done tests of shock tubes and gets good agreement with the exact solution using strings. This shock tube is, of course, not in general relativity, but just special relativity. The other test application was a stable TOV star. And here we just, for simplicity, used a gamma equals 2, m equals 1.4 solar masses, a case that has been done way back in the past in order to compare with things. And so we evolved that with 500,000 particles, 1 million and 2 million particles, and we can look at the oscillations of, and the oscillations here are triggered only by truncation error. We don't add anything in addition to that. But you can see that the oscillations are converging, converging away at higher resolution, getting smaller, the amplitude. And when we do Fourier composition, decomposition of the oscillations, we find to very good accuracy the frequencies up to, well, the fundamental modes, first order tone, second, third, fourth, and have a small indication with that we have a fifth one. And compared to the original paper, we needed to get some additional frequencies calculated by a student of Nick Stagulis. And so what I show here is the particle distribution of this TOV star after evolving it for 30 milliseconds. And you can see the horizon, the surface is still well behaved and everything looks fine. And if I look at the radial profile of the density as a function of radius, you can see that the only thing that has changed is that the particle that was at the outer boundary have moved in a little bit. This might be just because of the oscillations, but typically we see that. So everything seems to be working fine. Then I will show some results from a merger of a binary neutron star using the APR3 piecewise polytropic equation of state, 2 times 1.3 solar masses using 2 million particles. Here is just some plots of the density we're essentially at initial contact here, and then after some time. But what I was more interested, what I really want to show is, first I'll just show you that we can plot the density and lapse, and we see that it settles down to a long-lived remnant. We have extracted Wildescale 4 from the Einstein toolkits, the routine to calculate those, and we can then extract Psi4 from our simulations and then use Qubit to get the strain, and this is just an example of the waveforms that we get. But what is really cool is that if you plot the velocity of all the particles as a function of radius, you can see that there's kind of, in this case, 3 clear sort of arms of the long tail here. So we have our first wave of ejected particles, we have a second wave, and then a third wave. And with HPH, it's very easy to just color code these in the final plot, and then we can see where they originate from the point of collision and so on. And what I want to show here is that, well, first of all, over here we just plot things in the XY plane, and here is in the XZ plane, so we can see the polar direction as well. And so, okay.
The plots that you have in the panel on the right.
Yeah.
Are those the particles?
Those are individual particles. No.
Then you put the kernel these 300 particles. So out of particles that are outside, how do you manage to keep the 300? You will have to reach out to where the star is.
That is, well, okay, so the question is how we can keep the same number of neighbors for particles that are sort of moving out here. And yeah, we have to increase the smooth length. And
but if you increase it such a way that it starts touching the red thing,
yeah,
then you're gonna get an artificial gradient of the kernel. You have a highly homogeneous distribution of particles within the kernel.
in principle, as well, you're correct, but you also have to remember that the kernel sort of goes to zero fairly quickly. So these things actually contribute a lot less than you might think.
The other thing is that if you make it too large, the differences of the metric of the particle are going to be huge.
Yeah.
And that I think is an artificial force, right?
Yeah, but again, this is something that it will converge away when you add more particles. I mean, yeah, I mean, you do make an error in not taking into account the metric, but something that will converge away. So you can sort of divide these particles into something that is sprayed immediately at the first contact, and then you have the core contracting and then expanding again. And in the expansion, you actually have particles that get bounced back up at high velocity. And it actually turns out that the bounce actually produces higher velocities than the initial spray coming from the immediate contact. And in this case, the core bounces again, and so you get a third peak here. And so if you look here, I mean, you can see that when you go to later and later times, the red particles that are moving the fastest are starting to overtake some of the blue particles from here. And you can actually see that the blue particles are more concentrated in the plane, whereas the red and light blue particles are more spherical in that distribution. You can also color code differently. You can just select everything that has a velocity larger than 0.6 times c, and bin them in that way. And then you can actually see that some of the some of the red particle, in this case, some of the red particles are from the first spray, whereas the red particles further back here, if I continue, are actually particles that it starts moving out, but then falls back in, and then it hits the bouncing core, and then really gets ejected. And those are actually some of the particles that gets to some of the highest velocities, which is kind of interesting. Let's see. Yeah. Okay. So then we also did simulations where we had one neutron star that was spinning rapidly, a chi of 0.5. And if we plot those are also 1.3 solar masses, but because of the spin, the second star is larger in the xy plane, and this is flattened a bit in the z direction. So this star will then feel a larger tidal interaction with the other star, and so that is what we see here. That the spinning star, even though they have the same mass, actually gets tidally disrupted by the other star. Here I'm just showing results from 3 different resolutions: a soft equation state, harder equation state, and the hardest equation state we have looked at. And this really affects the amount of material that gets ejected. If we look at here we are comparing the solid curves are from the non-spinning case, where both stars are non-spinning, and we only get maybe 2.5 or 0.25% of the material being ejected in this case, whereas with the spinning black hole or spinning neutron star, we increase the amount of material that gets ejected by up to 1.5 to 2.5%. Yep. So you're asking if we had done different resolutions of these? Yeah, I mean, so even though this works well, I have to say that we cannot claim yet to be in the fully convergent regime yet, because the code is currently only OpenMP parallel, and so we can only run on one node at a time, and so these ones with many particles takes a really long time. So what I've tried to select for this talk was sort of things that are pretty solid and that we see consistently across our resolutions, but I wouldn't yet claim that we can do a comparison like that. But we are working on it. But the important thing is that with this, when most of the material that gets ejected here by the tidal interaction has then not been shock heated and would probably have an electron fraction that is close to the original material of the neutron star, whereas most of the materials have gone through some collision and shocks here, and so these would most likely produce very likely colored kilonova, and so this is something we want to take a closer look at. Then I just wanted to show you that we can also handle the collapse, the prompt collapse of two neutron stars. Here we have 2 times 1.5 solar masses, where we you can see that the density starts increasing rapidly. We have a scheme. We don't yet have an apparent horizon finder, but we use the lapse as a measure and tries to convert particles into dust until they get to a very low value of the lapse in order to continue our simulations without paying the ultimate price of the time step going almost to 0 because the particles get really close together. But this seems to be working okay, and we can actually extract waveforms where we see a little bit of stuff that you wouldn't see in a binary black hole simulation. Let me just, before going to that, let me just show you, let's see. Okay, so here is a movie of the collapsing case, prompt collapsing case, 2 times 1.5 solar masses. And let me just step through it here as best as I can. You see there's absolutely nothing going on between the between the neutron stars until the particles at the tip start to. And here you can see Kelvin-Helmholtz instability. Maybe not as clear, but and then this one just collapses immediately, and we calculate collapses so fast that we can start removing particles. And at the end, we have maybe 10⁻⁴ solar mass of material outside. But we still have material in this case where that escapes at velocities between 0.6 and 0.7 times the speed of light. So even in a prompt collapse, we still see a very small amount at high velocity material. So let me just go back here. And I think I'm also probably out of time anyway.
Well, we're going to extend 5 minutes. Sorry, just like,
Okay.
We still have 4 minutes.
Okay. So there's many things I haven't mentioned in the talk, and that is setting up initial data is non-trivial because you have to not only populate the grid with the space with the information about the space-time the metric variables, but you also have to place particles to best represent the density distribution that is present in the initial data that you're importing. And for that, we use something called an artificial pressure method, where you set up your initial data with assigning masses to particles in some positions. Then you measure the error you get when you evaluate the density compared to what you want, and you convert that error into a pressure that can then move the particles. And we move them around to something that where it looks like something like that. And as I said, we cannot yet claim to be in convergent regime. As I said, we have only OpenMP parallelization, but distributed memory parallelization is on the way using co-array Fortran. I've already got the grid parallelized. I mean, I still need to probably optimize it, but at least I'm able to, on a NUMA mode, I'm able to improve the performance compared to pure OpenMP by using 4 images in co-array Fortran that each uses OpenMP internally. It's simply because the memory access are better. Currently, the mesh refinement is really fixed mesh refinement. I place the coarse grid and a fine grid and a finer, and finer, and they just don't move under the doing the simulation. So in order to keep the binary, well, we usually try to keep the grid large enough that both neutron stars on the finest grid initially. but we should be able to reduce the cost of the mesh refinement space-time evolution by using moving grids. We said we don't have yet an apparent horizon finder, so I plan to interface it with Bahaha. Support for more equation of state, for example, tabulated, is something that Stefan is currently working on. The idea is that eventually we want to, when things have settled down, that we want to extract the particles and move them on a background space-time for continued evolution to make contact with the kilonova signals. And we have to improve our way of doing that mapping. And we also need neutrino transport, of course. It's been a big theme at this meeting here. So because you need that in order to know what the electron fraction of the ejected material is, and in order to produce reliable light curves. And maybe eventually MHD. Stefan doesn't seem to be too keen on doing that right now. He thinks the neutrinos are more important for now. But let me just stop here.
Any questions in the audience? I don't see any questions online either.
Oh.
So, there's a question.
One thing I'm curious about would be like, once you're able to make convergence tests, let's say for the spot.
Yeah.
Just to define like how convergence works. One thing I was wondering in that context is squeeze investigation with like F modes, G modes. Those are really bad. G modes dissipate a lot in the surface.
Okay.
You use, I don't know what it's.
Well, I mean, okay, so Elias was asking about F and G modes and their dissipation near surface of stars. Okay.
Like if you basically just ask like how well energy surface, right? You do the grid-based code, at some point you start dissipating surface.
Yeah.
Depending on how you do that stuff. Wondering like here, if you were to do this simple experiment, if the star is something that's not radial, but which path is close to the surface, how long does it do that?
Okay, yeah. So he's asking how, if we could set up an experiment where we have a neutron star with a shearing surface and see how well it maintains that. I haven't thought about that, and so obviously we haven't done it yet, but certainly something to look into, possibly. I mean, certainly we have less accuracy near the surface because we have less particles. The smooth lengths are larger, but yeah, that would be interesting.
So there's speaking time. I'll suggest that we further discussions outside. Let's be it again.
Oh, probably need to.
The next speaker will be Vasilius. He's going to be talking to us about neutrino radiation with black